Imagine you're standing at like this really upscale auction house.
Okay, I'm picturing it.
Right. And on the block is an item, and the auctioneer looks out at the crowd and tells you that what you are about to bid on is, well, the only one of its kind.
Like the last one left?
No, they make that clear. They don't mean it's the last one left. They mean it is the only one that has ever been found on planet Earth.
Oh.
Yeah. How much would you pay for absolute extreme rarity? I mean, how do you even put a price tag on a literal statistical impossibility?
You really can't, right? It's priceless.
Exactly. And welcome to today's deep dive. We are taking you on this wild journey into the concept of extreme geological rarity.
It is a mind-blowing topic.
It really is. And we've got a fascinating stack of sources for you today. We're pulling from some pretty dense geological research papers, including this highly detailed isotopic study on zirconolite growth.
Which is way more exciting than it sounds, I promise.
Oh, totally. Alongside that, we have some market analysis on a gemstone called painite, and this great piece from ZME Science on the discovery of a stone called kyathwite.
The kyathwite story is just, well, it's incredible.
It really is. So our mission today is to transport you to the Valley of Rubies in Myanmar. We are going to unpack the intense subterranean violence that forged the rarest minerals on Earth.
And then, of course, confront the very human reality of actually pulling those minerals out of the ground.
Right. Okay, let's unpack this. I want you to picture the scene.
Setting the stage.
Yeah, so it's the Changi Valley near Mogok in Myanmar. The year is 2010.
Okay.
Sapphire hunters are out there. They're sifting through the dirt and the gravel, basically looking for that familiar flash of blue.
Right, just doing their standard day-to-day mining.
Exactly. And they are bypassing countless ordinary stones, polished by water and time. But sitting right there in the rough, entirely overlooked, is this tiny reddish-orange crystal.
Yeah, and to the untrained eye, I mean, that stone looked like absolute river gravel. Just junk.
Really, just like standard gravel.
Basically. But it was eventually identified by mineralogist Dr. Kaya Thu. And later in 2015, the International Mineralogical Association officially recognized it as a brand new mineral.
Naming it kyathwite.
Right, naming it kyathwite. And when we talk about extreme rarity in mineralogy, we really have to be incredibly precise here. There is exactly one specimen of kyathwite known to science.
One.
Yeah.
Just one single crystal. And it weighs 1.61 carats.
Which is tiny.
Yeah, that's roughly 0.3 grams. And right now, it currently sits completely alone in a museum case in the Natural History Museum of Los Angeles County.
It's kind of lonely when you think about it.
It is. And structurally, looking at our sources, it's a bismuth antimony oxide, and it carries traces of tantalum.
Yeah, that chemical makeup is bizarre.
Right. And our sources note it has this strange checkerboard pattern of antimony and oxygen sheets nested against bismuth atoms.
And what's fascinating here is that internal structure is precisely why it is so unique.
Because of the checkerboard thing.
Yeah, because bismuth and antimony are heavy metals, right? But they don't typically combine with oxygen in this specific alternating arrangement.
Okay, so when they do, what happens?
Well, when they do, the atomic packing becomes incredibly dense. The checkerboard lattice allows these heavy atoms to nestle so tightly together that the resulting stone actually has a density 8 times that of water.
8 times. That's insane.
It really is. And to understand how something like this even forms, we have to look at its origin in pegmatite.
Okay, wait. Pegmatite is an igneous rock, right? Like the stuff that forms from cooling magma.
It is, yeah. But pegmatites are special. They form during the very, very late stages of magma crystallization.
Like the leftovers.
Exactly. Think of it as the dregs of a geological soup. When a massive body of magma slowly cools underground, the really common elements, like quartz and feldspar, they crystallize first.
Right, they take up all the normal slots.
Exactly. So what gets left behind in that final liquid portion of the magma is this highly concentrated sludge of all the weird, incompatible elements that just didn't fit into the standard rocks.
Elements like the bismuth and antimony and tantalum.
Precisely. They're all forced together at the very end.
So it's not even the typical dark matter needle in a burning haystack analogy that people usually use for rarity.
No, it's way more specific than that.
It's more like, I don't know, throwing a shuffled deck of cards into the air and having only the heaviest cards land perfectly assembled into a 5-story house of cards.
That is a great way to put it.
Right, because you need the exact chemical leftovers cooling at a painfully specific rate, under the perfect pressure, just to get this one microscopic crystal.
And that house of cards is incredibly fragile during its formation, too. Like if the temperature fluctuates by just a few degrees, or if, say, a different fluid washes through the rock.
It ruins the whole thing.
Yeah, you don't get kyathwheat, you get a completely different, much more common mineral.
Wow. Which actually answers a question I had when I was looking at the source material.
Oh, what was that?
Well, if this thing is only 0.3 grams, and it's surrounded by literal thousands of ordinary sapphires and spinels in that riverbed, a miner shouldn't have ever noticed it.
Right, it should have been tossed out.
Exactly. But if it's 8 times denser than water, a stone that tiny would feel entirely wrong in the hand.
Yes.
It would feel like a little lead weight, you know. A seasoned miner wouldn't need a lab to tell them they were holding an anomaly.
That is exactly it. The intuitive expertise of the people working that dirt is really the only reason science has this specimen today.
Because they just knew it felt off.
Right. That slight unusual heft, combined with a reddish-orange hue that just didn't quite match the local rubies, it flagged it as something requiring closer inspection.
That's wild. But, you know, if Cothwaite is a total geological fluke that only happened once, it makes you wonder what happens when a fluke scales up just about to become a commodity.
Yeah, moving from one to a few.
Right. Which brings us to another mineral from this exact same patch of dirt that actually used to hold the title of world's rarest, but has since exploded into this booming high-stakes market. Painite.
Painite.
Right.
Yeah, discovered in the 1950s by a British mineralogist named Arthur C.D. Payne.
And for a long time, there were barely any, right?
Decades, yeah. For decades, painite was basically the holy grail of mineralogy. Up until the early 2000s, there were fewer than a dozen known specimens in the entire world.
Less than a dozen.
Yeah.
But our market analysis sources show that thanks to a massive surge in mining over the last 20 years, that number has gone up.
Though up is highly relative here.
Oh, completely relative.
Yeah.
As of last year, fewer than 1,000 painite crystals are known to exist globally.
Still incredibly rare.
Very. And the price tag reflects that. High-quality stones can reach up to $60,000 per carat.
It's staggering.
It is. And this stone, it's a bizarre cocktail of elements, too. Calcium, zirconium, aluminum, boron, and oxygen. It has a Mohs hardness of 8, which means it easily scratches glass. And it comes in these deep reddish brown and orange colors.
And you know, the scientific community pays very close attention to that specific chemical composition.
Really? Why the intense focus?
Well, painite is a borate mineral, meaning it contains a structural framework of boron and oxygen, and borates have immense technological intrigue.
Oh, like for electronics.
Exactly. They are actively researched for potential applications in advanced optics, lasers, and semiconductors.
The lasers?
Yeah, because their crystal lattice handles light and thermal expansion in highly specific, very useful ways.
Okay, here's where it gets really interesting. Because if painite is scoring an 8 on the Mohs scale, making it super durable,
Right.
and it has all this advanced technological potential for directing lasers, it seems like we should be utilizing it in tech.
You would think so.
But we're only putting it in bespoke jewelry or locking it up in museum vaults. I'd hypothesize that if it's that structurally useful, tech companies could just synthesize a lab-grown version of that calcium, zirconium, boron lattice and put it in our smartphones.
Synthesizing it is theoretically possible, yeah. But the market value of painite is completely divorced from its industrial utility.
So they don't care about the lasers.
Not at all. The people driving the price up to $60,000 a carat aren't buying it for what it can do inside a machine.
Who is buying it then?
The value is sustained by high net worth collectors, investors looking for non-correlated tangible assets, and actually a highly dedicated metaphysical market.
Metaphysical, like crystal healing type stuff.
Yeah, spiritual enthusiasts. They associate painite with profound transformation, viewing its creation under intense geological pressure as a literal manifestation of resilience.
Oh, wow. So synthesizing it in a lab would actually destroy the value proposition for that target buyer.
Completely.
They are paying for the deep Earth origin story. They're literally paying for the scarcity.
Precisely. The allure is that the Earth somehow managed to forge fewer than 1,000 of these under incredibly violent conditions.
Which is a perfect segue, because both of these stones, the singular kyathwheat and the $60,000 painite, they both come from the exact same region.
The Mogok Metamorphic Belt.
Yes, frequently called the Valley of Rubies.
Yeah.
We have to dig into why this one specific patch of dirt in Myanmar is producing chemical combinations that simply do not exist anywhere else on the planet.
And to grasp the scale of what happened there, we really need to look far back in deep time at a literal subterranean pressure cooker.
How far back are we talking?
Around 150 million years ago, during the Cretaceous period, a massive tectonic plate known as the Burma Block violently collided with the Shan Plateau.
Okay.
And following that, roughly 50 to 20 million years ago, the Indian Block just smashed into the entire region.
So we're talking about entire continents folding and piling up on top of each other, just crushing whatever rock happens to be caught in the middle.
Exactly. And caught in the middle of that crush was a wildly diverse geological jumble.
Like what?
Well, the source papers detail a mix of cyanites, metasediments, massive limestone deposits, and skarns.
Wait, hold on. You just threw a lot of heavy geology at me all at once.
My apologies, I get carried away.
No, it's great. But for those of us without a geology degree, if I'm looking at a cross-section of the Earth there, what exactly are cyanites and skarns? Let's define the ingredients in this tectonic blender.
Fair point, yeah. So cyanite is an igneous rock, very similar to granite, but crucially, it lacks quartz.
Okay, no quartz. Got it.
Metasediments are just old sedimentary rocks, like mud or sand, that have been baked and pressurized until they change form completely.
Makes sense. And skarns?
Skarns are essentially chemical battlegrounds.
Battlegrounds.
Yeah, when super hot magma intrudes into a cool limestone deposit, it bakes the limestone, right?
Yeah.
And it creates a contact zone where intense chemical reactions occur. That chaotic reaction zone is a skarn.
So all of this is being mashed together under continents. And the limestone specifically gets crushed and baked so thoroughly that it turns into a ruby-bearing marble, which the locals actually call gega.
Yes, and that marble is the primary host rock for many of these rare gems. It provides the essential calcium and aluminum base.
But, plates collide all over the world.
They do.
I mean, the Himalayas are right next door, born from that exact same Indian block collision. But the Himalayas aren't spitting out painite and kythowite. What makes Mogok unique? It can't just be pressure.
No, you're right. Pressure and heat alone just give you standard metamorphic rock. Mogok is unique because of highly reactive superheated fluids.
Fluids deep underground.
Yeah. When those magma intrusions baked the limestone into marble, they didn't just provide heat, they released waves of mineral-rich water and gas.
Oh, I see.
These fluids infiltrated the marble under immense pressure, essentially acting as a chemical delivery system. The marble had the calcium and aluminum ready, but the invading fluids brought the bizarre, rare elements like zirconium and boron.
So if you were holding a piece of this marble in your hand, you'd basically be holding a sponge that got power washed with rare earth metals while inside a pizza oven.
That is a highly vivid but remarkably accurate way to describe it.
And the incredible thing about our source material here is that geologists don't have to guess that this happened. They don't just theorize.
They have proof.
They can literally track the exact timeline of these chemical fluid lasts using microscopic time machines trapped in the rock called zirconolite.
The zirconolite record is honestly a brilliant piece of geochemical detective work.
What exactly is it?
Zirconolite is an accessory mineral found scattered throughout the Mogok dolomite marbles. And an accessory mineral just means it's present in tiny, tiny amounts, so it's not making up the bulk of the rock.
Okay, just little specks here and there.
Right. Its ideal formula is calcium, zirconium, titanium, and oxygen. But the key to its role as a time machine is its crystal lattice, which is incredibly accommodating to uranium and thorium.
And because uranium is fundamentally unstable, it decays into lead at a very predictable fixed rate over millions of years.
Exactly.
So when the zirconolite crystallizes, it locks in the uranium but rejects lead. So any lead found inside that crystal today must be the result of uranium decay. That's UPB or uranium lead dating, right?
Spot on. By firing lasers at these microscopic zirconolite crystals and measuring that exact ratio of uranium to lead, scientists can actually read the chemical diary of the Mogok Metamorphic belt.
It's amazing.
The papers outline 3 distinct types of zirconolite, which prove there were 3 massive separate episodes of fluid infiltration over a 15 million year period.
So it basically functions exactly like a geological USB drive.
Yes.
The rock gets hit with a wave of superheated fluid. It crystallizes the zirconolite, which essentially hits save on the date and the exact chemical recipe of the fluid, and then it just waits underground for millions of years until we plug it into a mass spectrometer.
And if we connect this to the bigger picture, the data on that drive is remarkably detailed.
What does it tell us?
Well, stage 1 happened roughly 35 million years ago. A fluid highly enriched in uranium, thorium, zirconium, and titanium swept through the marble, creating what researchers classify as Zirol-1.
Okay, that's wave one.
Then, shortly after, in stage 2, there was a local fluid-assisted dissolution-precipitation event.
Let me make sure I understand that term, dissolution-precipitation.
Sure.
That means the second wave of fluid didn't just melt the existing zirconolite, it acted more like a microscopic renovation, like
Yeah.
dissolving the outer layer of the crystal and instantly rebuilding it with new chemicals from the fluid, right?
That is the exact mechanism. It creates a distinct core and rim zonation, which scientists categorized as Zirol-2.
So an older core with a new rim.
You got it. Finally, around 19 million years ago, stage 3 occurred. A totally different silica-rich fluid infiltrated the area, breaking down a zirconium oxide mineral called baddeleyite.
And what did that make?
It formed Zirol-free coronas, which are essentially little crowns of new zirconolite growing around the remnants of older minerals.
That paints an incredibly violent picture. Just 3 distinct, massive waves of fluid tearing through solid rock.
Extremely violent, yes.
But reading through the research, there's a physical problem here that they mentioned. Rare metals like zirconium and titanium are high field strength elements.
Right, they are notoriously insoluble.
Exactly. They shouldn't be surfing around freely in underground fluids. They should be anchored in place. So how are they moving?
The insolubility of high field strength elements baffled geologists for a long time. If they can't dissolve in water, how did they get injected into the marble to form painite and zirconolite in the first place?
Right.
The research points to a very specific chemical getaway car, basically. Fluorine.
Fluorine acting as the transport vehicle.
Yes. Geologists analyzed nearby minerals, specifically a type of mica called phlogopite, and found unusually high concentrations of fluorine.
Okay, and what does the fluorine do?
When fluorine mixes into these superheated aqueous fluids, it acts as a complexing agent. It chemically bonds with those heavy, stubborn, rare metals, suddenly making them soluble.
Oh, wow.
It mobilizes them, allowing them to flow freely through the Earth's crust.
So the Earth literally used fluorine to hotwire heavy metals and transport the ingredients for these incredibly rare gems right through solid rock.
Pretty much.
And once the fluid cooled down, or reacted with the marble, the fluorine just dropped the metals and they crystallized into the stones we see today.
That's the geological magic trick.
Now, we've spent a lot of time talking about the extreme subterranean pressure required to forge these minerals millions of years ago. But shifting our focus to the present day, there's a vastly different, deeply human pressure required to pull them out of the ground.
There is. And now, as we get into the reality on the ground in Myanmar, it's really important to pause and tell you listening, our goal here isn't to take a political stance or endorse any side.
Definitely not.
We are simply looking objectively at the market reports and geopolitical analyses provided in the sources, and the facts on the ground are stark.
Very stark. Myanmar has faced decades of severe political instability. According to the reports, the last official legally recognized gemstone mining licenses expired in 2020.
Right.
Then following the military coup in 2021, the entire official gemstone mining sector became effectively illegal. But as we discussed with painite, a $60,000 per carat demand does not just vanish because of a legal decree.
No, the market always finds a way. The suspension of official mining created a massive void, which triggered an unprecedented boom in informal artisanal mining.
How big of a boom?
The reports indicate that tens of thousands of informal miners are now working in the Mogok region and Kachin state. These operations operate entirely outside of standard regulatory frameworks.
And who is overseeing them?
They are largely overseen by the military junta and various non-state armed groups.
And when you look at the conditions detailed in these reports, the human cost is heavy. Because this is entirely unregulated, miners are working in geologically unstable active tectonic zones with, like, hand tools and basic ear pumps.
It's incredibly dangerous.
It is. The sources cite widespread use of forced labor, severe child exploitation, and profound human rights abuses just to access these deep earth gravel beds.
And this situation forces a profound paradox onto the scientific and gemological communities.
How so?
Well, on one side of the ledger, stones like Kaihafleet and painite hold incalculable scientific value. They are literal data storage devices for understanding the Earth's geochemical history.
Right.
But on the other side, the human toll required to extract them creates a massive ethical barrier to actually acquiring them for study.
It totally grounds the conversation. Because when you see a high-quality painite crystal sparkling under the auction house lights, it is incredibly easy to fixate on the geometry and forget the bare hands that pulled it from the earth under perilous conditions.
There's a disconnect.
Yeah. And because of those conditions, many international buyers and major scientific institutions have instituted strict boycotts against materials sourced from Myanmar to avoid funding the exploitation.
But the market is attempting to navigate this immense ethical roadblock using modern tools. What kind of tools? The sources highlight technology companies like Pharmanaut. They're deploying a combination of satellite monitoring and blockchain technology to bring transparency to an intentionally opaque industry.
Satellites. Really?
Yeah, they utilize high-resolution satellites to monitor these artisanal mining zones from space, tracking environmental degradation and illegal expansion.
That's clever.
And simultaneously, they are attempting to use blockchain ledgers to verify the origin of stones and track the supply chain, trying to provide a pathway for ethical sourcing.
So it's an ambitious attempt to use 21st century digital architecture to solve a geopolitical human crisis built around 35-million-year-old rocks.
Exactly.
It really represents a staggering collision between deep time and modern reality.
It perfectly encapsulates why mineralogy is never just about chemistry. I mean, every single faceted gem from this region represents the violence of tectonic plates colliding, millions of years of subterranean fluid dynamics, and ultimately, human struggle.
Looking back at the whole picture we've painted today, we started with a single 1.61 carat crystal of kyathwite sitting alone in a museum in Los Angeles. The absolute definition of a one-of-a-kind statistical impossibility.
The only one on Earth.
Right. Then we traced the journey of painite from an obscure discovery in the 1950s to a booming metaphysical and collector market driven entirely by extreme scarcity. We dove into the tectonic crucible of the Mogok Metamorphic belt, watching as the Burma and Indian plates crushed continents together, injecting marble with fluorine-laced rare metals.
And we learned how to read that ancient geological diary using those microscopic zirconolite timekeepers, proving that this complex recipe was delivered in 3 distinct violent waves over 15 million years.
And finally, we confronted the modern truth that accessing these miracles of deep earth chemistry is inextricably linked to political instability, human suffering, and the urgent need for supply chain transparency.
It's a heavy but fascinating reality.
It is. It reminds you that true rarity isn't just about the price tag at an auction house. It's about the miraculous convergence of deep time, extreme chemistry, and human discovery.
Absolutely.
But before we wrap up this deep dive, I'm going to leave you with one final thought to mull over. Both kyathwite and painite were initially mistaken for ordinary stones.
Just river gravel.
Yeah. They sat in bags of rough gravel, entirely overlooked by seasoned miners and gemologists for years before someone finally realized they were holding something utterly unique.
Makes you think.
It really makes you wonder how many entirely unique, one-of-a-kind minerals are sitting right now in a museum backroom, a dusty private collection, or even in a cheap piece of costume jewelry you picked up at a thrift store, just waiting for someone to look a little closer. Could you already own the rarest thing on Earth?